Hi all. We're starting our Chapter 2 notes with the concepts of rates of change of tangent lines via limits. Now, the way that we're going to start off this section and try to get to the logic of a limit is through some examples here. And the examples I'll use are a physics example of throwing a rock off of a cliff. Notice I say here, you're standing on the edge of a cliff, unsure exactly how high it is, and you decide to drop a rock off the edge. Why would you do that? So you could have some math fun, and hopefully there's no one below, because that would just be cruel. Okay, so now, assuming that there's no one below, we're going to think of this function that's representing the distance. Now, our distance function, because the only thing that's going to be speeding up this rock, and I'm neglecting wind resistance here, is the force due to gravity. Now, this is an approximation of the force due to gravity here, but let's say that the position function is given by 16t squared. Okay, this is assuming that that the gravitational constant is 32 feet per second every second. Now, whenever we use this position function, I can then say, well, if I'm trying to answer a question about how far the rock has fallen after 5 seconds, I'm given a displacement or a position function at any time t. So all I have to do is, well, just plug a 5 into that. That's easy. We've done things like that since Algebra 1. So the position function evaluated at 5 would just be 16 times 5 squared. That's 16 times 25. I know after 5 seconds, the rock has fallen 400 feet. Okay, so then if I say, well, all right, let's find out how fast the rock has fallen after 7 seconds. Say it's the exact same function, 16 times 7 squared, that's going to be 16 times 49, I get 784 feet. Okay, now if I ask you what the average velocity over this 5 to 7 second time interval is, then you just say, okay, velocity is the change in distance over the change in time. Okay, so here's what I do. Average velocity is going to equal the ending position, which is 784 feet in this case, minus the beginning position. The beginning position of the interval I'm interested in is at 5 seconds, and it's at 400 feet at that point. We'll divide that by the ending time minus the beginning of time, or beginning time in this interval. So now, an abbreviation that's going to come up quite often in here, anytime you see me use AROC, that will always mean average rate of change. The velocity in this case is the average rate of change from 5 to 7 seconds. So yes, I'm finding velocity, but the velocity in this case is the average rate of change from 5 to 7 seconds, which is the position evaluated at 7 minus the position evaluated at 5, divided by the time differential, 7 minus 5 seconds. Clearly that time differential is 2 seconds. We know our numerator, ending position minus beginning position, is the 784 minus 400. So what we know here is over this 2 second time period, that rock has fallen 384 feet. So its average velocity over that time period would be 384 over 2, or 192 feet per second. Okay, now think with me just a second before I go on to the next page. We know that gravity is going to continually speed this rock up all the way on its path downward. So if I said, okay, if I ask you to just say higher or lower, what is the instantaneous velocity at 7 seconds? Hopefully you're thinking, well, it's going to be higher than that because it will have more time to speed up. Well, what would be the instantaneous velocity at the beginning of this period at 5 seconds? Probably be less than that. It just makes sense that the average velocity over this 5 to 7 second period, it's going to be faster than the velocity at 5, but slower than the velocity at 7. It's the average velocity over this time period. Okay, so now hypothetically, and I'll take the hypothetical away because it is my next question, What if I ask you to find the instantaneous velocity of this rock at 5 seconds? So I don't want the average rate of change. I want to know how fast is the rock going at 5 seconds. Well, what's the problem? I don't have a velocity function. I have a position function. And so here's the idea of it doesn't matter that we don't have a velocity function, because the average velocity is going to be change in position over the change in time. If I can make that time differential small enough, then that average velocity can get extremely close to approximating the instantaneous velocity at any certain amount of time. So notice what I do. If I want to know what the instantaneous velocity is at 5 seconds, then I'll find the average velocity from 5 to 5.1. I'll find the average velocity from 5 to 5.01. And I'll find the average velocity from 5 to 5.001. So notice, only a 1/10 of a second time differential here, a 100th of a second time differential here, and a 1,000th of a second time differential. So it's not going to get much time to speed up from 5 to only a 1,000th of a second later. So this last one should be pretty accurate. Now, with that said, that last one is still not going to give me my answer. I need to be looking for a pattern of what the limiting value is. So let me go back up here. The average rate of change from 5 to 5.1. You would plug a 5.1 into your function over here. You'd just say, well, it's 16 times 5.1 quantity squared. And when I did that, I got 416.16. I subtract the beginning position, which is always going to be 400 in this problem. The position at 5 is always 400. So I can see here, over that 1/10 of a second, it's traveled 16.16 feet. That gives me an average rate of change over that 1/10 of a second of 161.6 feet per second. Now, when I try to narrow my time interval to 100th of a second, I have to say, well, I need to find the position of the particle at 5.01, or the rock, I should say, at 5.01, minus the original position at 5 over my time differential here. Well, when I try to find the position of the rock at 5.01, I just plug 5.01 into that equation. And by the way, I would recommend plugging these into your equations like this. Now, it's not hard for this one since this is such a simplistic one. You can see where I've done another problem like this too. Problems that are going to require many different values for x, and if you want to do them on the home screen, what I would just recommend, and remember any variable can be x, so technically the variable in this problem is t, but I'll call it x on the home screen. All I would have to do if I wanted to find out 5.01 is I'll type in 5.01. I'll store that in. The store button is right here. I'll store that in for x. And now I want to do a colon to type in the equation. Colon is alpha decimal. You can see the colon right there. Pops up. Now just type in your equation. Well, my equation is just simply 16x squared here to represent 16t squared. So when I plug the 5.01 in, yes, I get the ending time, or the ending position for the time of 5.01. Now, if I wanted to go ahead and do the one in the next problem, no big deal. I would just go second enter, change the 5.01, insert in. I hit second delete to insert in another 0, and boom. I have the value at 5.01. It's going to be 400.160016. Now, you don't have to do it that way. However you do it, just make sure you get your numbers in here correctly. I just thought that was kind of a cool trick that will help us later on in the class when we use a method called Newton's method. We'll have to use that storing technique. So it's probably good to go ahead and get used to using it. Now, however you get these values in, you plug them into your formulas. And here in this case, I can see, well, over this 1/100th of a time second interval, I see that my position has, or that the rock has moved 1.6016 feet in the 1/100th of a second. So that means it's moving at an average velocity of 160.16 feet per second. Now, as soon as you get two average velocities, you should be trying to look for patterns here. And I can already see a pattern, and hopefully you can too. Look at what's the difference between this number and this number. You say, well, they're all the same digits except there's a 0 in between this 6 and this 1. So instead of 161.6, it's 160.16. So I've already done the next one, but if I were just to guess, well, I wonder if that pattern's going to continue. What should I expect the next number to be? I expect there to be another 0 in between this 6 and this 1, so I expect it to be 160.016. Now I'll go ahead and show, glorious, oh glorious, 160.016. That pattern does emerge. So I can see, okay, the more I narrow this time interval, 1/10 of a second, 100th of a second, 1,000th of a second, here at 1,000th of a second, it only moved 0.160016 feet. But when you divide that by the 1,000th of a second, you can see that your average velocity is 160.016. By the way, please do not round any of these numbers or that pattern will not emerge. You're going to have a rounding error in your answers, and you're just going to be confused as to what the answers are. But in this case, keeping all decimal places within the problem, I can see, yeah, this is going to have a nice limiting value. The smaller this time interval gets, the closer that second time gets to 5. So if I were to say, hey guys, what's the average rate of change from 5 to 1/10,000th of a second later, 5.0001? I guarantee you it's going to be 160.0016. And then you say, okay, then what value is that approaching? Well, if you kept on reducing that time interval, it's going to be 160 point as many zeros as you want. Well, and that number is going to be approaching 160. So that's what I'm saying here. What do these average velocity calculations over smaller time intervals get close to? This is the calculus concept of a limit. I need you to see the limiting value is not any one of these specific values. These are all average rates of change. These are average velocities. Even this last one, it's still the average velocity over 1/1000th of a second. But I want to know at the instant of 5 seconds, how fast is it going? It's going 160 feet per second. Now, the way I would denote these calculations that I've done up here above, this is a limit. What I'm doing is I'm taking this second time and I'm putting it ever and ever closer to my first one, 5.1, 5.0, 5.001. All of these are approaching 5. So notice my limit notation here. I'm saying I'm going to take my function s of t and I'm going to plug values of t into it that are approaching 5 from the right. That's what this means. This is the limit as t approaches 5 from the right. So all of my values that I'm going to plug in for my time are values approaching 5 from the right. They're getting closer and closer to 5. Well, my second value is always s of 5. Notice it's consistent in there. I always subtract the beginning position, which is always s of 5. So my ending position is evaluated at a value of t that's getting closer and closer to 5, minus the position at 5, over my time differential, which is again going to be t minus 5, as that value of t is getting closer and closer and closer to 5. It started at 5.1, 5.01, 5.001. So please notice how this limit notation represents what we've done up here. Now, this limit notation is going to give us what the instantaneous rate of change of this position function at 5 is, or in other words, the instantaneous velocity. When I ask you whether I say what's these average calculations approaching, 160 feet per second, well, how fast is the rock moving? That's just another way of asking the exact same question, 160 feet per second. Now, in general, anytime we want the instantaneous velocity, before we're able to take the derivative will give us the instantaneous rate of change. But for now, we have to do an algebraic solution. And you can say, well, with the algebraic solution, we're just going to have to think of this limit. If I want to know the instantaneous velocity at some time period t sub 0, then I'll have to take a second time, I'll call it t sub 1, and I'm going to have to force that t sub 1 to get as close to t sub 0 as I possibly can, and then I'll just say, well, it's just the change in position over the change in time. As that change in time and change in position get very, 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 very small. That's, hopefully you see, that's what I did in these problems. This is the change in position over the change in time. My times got very, very close to one another. That's what's happening here. T1 is approaching T0. Well, that's approaching T sub 0. That's approaching T sub 0. So I can say my numerator, the position at time T1 will be approaching the position at time T sub 0. Look how close these positions got to one another, because it just makes sense. If your time interval is going to shrink, clearly it's not going to have as long to travel as much of a distance. Okay, up next, let's look at another one with this problem. I started off on the first page saying that we knew just from using physics logic that if the average velocity from 5 to 7 was 192, we knew that the instantaneous velocity at 5 was less than that, and we knew that the instantaneous velocity at 7 had to be more than that. Now, we've already found the instantaneous velocity at 5. It certainly was less than that. It was 32 feet per second less. Well, okay, what about the instantaneous velocity at 7? Well, we know it's got to be more than 192 feet per second because that was the average velocity. If I wanted to find out, then I can say, well, since I can't use a derivative right now, I have to show it with algebraic limits. And so if I'm trying to find out what's happening at 7, I'll find a time interval, and usually I always do 1/10 of a second, 100th of a second, and 1,000th of a second. Those are really good ways to find a pattern for what emerges in the problem. So I'm going to find the average rate of change from 7 to 1/10 of a second later, and then from 7 to 100th of a second later, and then from 7 to 1,000th of a second later, and there should be a pattern that emerges in my answers. Now, and this 7.01 didn't show up very well there, but this is S of 7.01, the ink smeared. So when I'm looking at this one, I can say for this first one between 7 and 7.1, the position at 7.1 gave me 806.56. Minus my initial position is now at 7. Please remember that was back here on the first page where we did 16 times 7 squared. We had, well, the position at 7 was 784 feet. So we can see over this 1/10 of a second, that rock has traveled 22.56 feet in a 1/10 of a second time span, which gives us 225.6 feet per second on average velocity. Okay. Now, if I say, yeah, but I'm not sure that that's accurate because it's had time to speed up over that 1/10 of a second. So I know my true velocity at 7, or my instantaneous velocity at 7, it's less than that because it's had a 1/10 of a second time to speed up to find this average velocity. So I say, well, what about 100th of a second? And I'll have to go back in and rewrite this. This is S of 7.01 minus S of 7 over 7.01 minus 7. When I put in S of 7.01, I got the 786.2416. And again, remember, super easy to do that. All you had to do is bring that up. If I wanted to change the 5.001 to 7.01, no problem. I'll delete off that one. Boom. There's your number, the 786.2416. So now I can see, well, the rock has traveled 2.2416 feet in the spans of time of a 100th of a second. We divide that out, it's traveling 224.16 feet per second. So if I try to look for this to try to see a pattern, I can see, well, it's dropped about 1.44 feet per second. Now, I know that it's never going to change that dramatically again. If I had to guess what the next one is going to change, instead of dropping 1.44 feet per second, I think it will drop 0.144 feet per second. Because if I move a decimal place here, my change is probably going to change a decimal place. Let's go look. So now between 7 and 7.001, the position at 7.001 gave me 784.224016. Please don't make any rounding error on that. Take all the decimals out. Minus 784 over 0.001. I see my numerator is 0.224016 divided by 0.001. That's giving me an average velocity of 224.016. Now, it's actually, and the pattern I said here does still hold. It's this minus 0.144, but it's even easier than that. Now I can see, oh, from here to here, and from any other, if I went from 7 to 7.3 zeros in a 1 or 4 zeros in a 1, I can see what's going to happen now. It's going to continue to add another 0 between this 4 and this 1. Here I have 224.16. Here I have 224.016. If I said, well, what's going to be the average velocity between 7 and 1/10,000th of a second later? I guarantee it'd be 224.0016. So then the question is, we don't want these average velocities. Each of these are average velocities. What number is this getting closer and closer to as this time interval gets very close to each other? So as your time interval becomes 0 seconds differential, what is this instantaneous velocity, or this average velocity, going to give us for the instantaneous velocity? And hopefully you see, well, it's going to approach 224 feet per second. We would say that the velocity, or the instantaneous rate of change at 7 seconds, is 224 feet per second. That would be the limiting value. Now, again, if this doesn't convince you, you can keep on doing these. So if you want to go to 1/10,000th or 100,000th of a second differential to keep on seeing how these times reduce to this, you can. But I just don't want you spending too much time on these problems. Up next here, I started off titling the section Tangent Lines and Rates of Change. So where the tangent line comes in here, tangent line is going to be a line that touches a curve at one point, and it is going to take on the instantaneous rate of change. Before we talk about tangent lines specifically, let's talk about another type of line called a secant line. Now, I changed the notes a little bit. I believe it was x equals 0 and x equals 1 here, but I whited it out. Just for a better graphical representation, I want to calculate the average rate of change, or the average slope, between x equals -2 and x equals 3. Okay, so first of all, I want to go ahead and sketch a graph, and then I'll talk about the average rate of change. So I plugged in f of -2, and I got -2 squared plus 4 times -2. That's going to be 4 minus 8 for -4. F of 3 is going to be 9 plus 12 for 21. Now, just looking at this parabola, you know it would factor to x times x plus 4. So it's going to have x-intercepts at -4 and 0. That's what I wanted to go ahead and do. I know it has an x-intercept at -4 and 0, which means its vertex is going to be right in between. Well, right in between is our value f of -2, which we know is -4. So I'll go ahead and draw that vertex in, and then I know my function is going to go up. I know that when x is 3, my y value is 21, so I went ahead and plotted that point. Now, the reason I wanted to draw the graph here is because the same thing we've been doing above with these average rates of change, if I said I just want you to find the average rate of change of that function, well, the slope of the line connecting these 2 points on the curve would be the slope of the, the slope of that line would be the average rate of change. Remember, slope is just the change in y over the change in x. So if I said, hey guys, I want you to find the slope from this point to this point, you just say, well, it's y2 minus y1 over x2 minus x1. 21 minus a -4 over 3 minus a -2. That's the exact same thing you do when we're doing our average rate of change formulas. If I say, show me what the average rate of change is from -2 to 3, you'd say, well, it's the ending position minus the beginning position, which is f of 3 minus f of -2 over the end position minus beginning position, 3 minus -2 in terms of x. So I can say, well, this is the exact same thing as the slope of this of the line connecting those 2 points. I get my 21 minus a negative 4 over 5, simplifies down to 5. The slope of that black line, it's going up 5 y units per x units there. Well, that's its average rate of change. So the slope between any 2 points is always an average rate of change. Now, something else that I want to come up with just for a vocabulary term, anytime you connect 2 points on the graph of a line, it does give you the average rate of change of the graph over the period where those 2 points are. And that line is called a secant line. I know that the slope of the secant line, so a secant line is just a line that connects 2 points on any curve. That's the secant line to this quadratic function between -2 and 3. And the graph of that secant line, the slope of it would give me the average rate of change of my function over this period. So I can see, well, all right, at 3, if I said, does your function grow more quickly or less quickly at 3 than it does on average from -2 to 3? Well, I can tell that the slope of my quadratic is steeper than the slope of this black line there. So I can say, well, it's going up more quickly here. What about at -2? Well, at -2, it's flattening out because you've hit the vertex there. It has a 0 slope, and then only after that do you start increasing. So you'd say it starts off way lower slope than this average rate of change. But on average, from -2 to 3, the slope of that black line is going to tell you what happens between -2 and 3 on that function. Now, let's try to think a little bit more. I was talking about the slope at 3 over here just a minute ago and saying, well, the slope at 3 is clearly steeper. And we know that the average rate of change from -2 to 3 was 5. I know the instantaneous rate of change at 3, it's more than 5. It's going up more quickly than that. Well, let's see. So on this page, and again, I changed it. I had a 0 planned in the notes, but I would rather look at what happens at 3. So I want to find the instantaneous rate of change at 3 on this function. So what I'll go in and do is I'll say, well, all right, I'm going to find the average rate of change from 3 to 3.1. So I'll go 1/10 of a unit away. Then I'll find the average rate of change from 3 to 3.01, 1/100th of a unit away. And then from 3 to 3.001, only 1,000th of a unit away. So in order to do these just real quickly, I could say, I could go ahead and get all of my values that I need here. Of course, the 3 you could plug in easily. That's just 3 squared plus 4 times, that's our 21. So that's that beginning point we shouldn't worry about. We know that that's going to be 21 in all of the problems. If I just really wanted real quickly to show where all those first values comes from, it just comes from plugging in a 3.1, a 3.01, and a 3.001 into my function. So I can say, well, I'll start with a 3.1, and I'm going to insert that by hitting the store button in for x, and then I'll hit colon alpha decimal. Now I type in my function. My function is just x squared plus 4x, x squared plus 4x there. Then I can say, all right, this will give me the 3.1. That's where I got my 22.01 from. If I want the 3.01, all I have to do is hit second enter, arrow back, plug in a 0 before the 1, and I see, okay, 21.1001. At 3.001, do this again, insert another 0, and I've got that, the 21.010001. So I just wanted to show you that real quick for how I got these values. Other than that, it's extremely straightforward. Now, so from 3 to 3.1, your y value went up 1.01 unit in the time the x value increased 0.1. So our slope in that region from 3 to 3.1, it's a slope of, it's going up 10.1 y units per x unit in that period. Okay, but we want to know more precisely what's happening at 3. We don't want the average rate of change from 3 to 3.1. So I can say, well, all right, try to find a smaller interval closer to 3, 1/100th of a unit. And you're not going to see the pattern if you don't try to do something like a 10th, a 100th, a 1,000th. That's a very good idea to establish a pattern. So notice, when I go to 100th of a unit away, I can say, well, now my y value has changed 0.1001 units as my x value changed 0.01 units. When I divide that out, I can see, well, now my slope is 10.01. That's the average rate of change from 3 to 3.01. That would be the slope of the secant line connecting x equals 3 and x equals 3.01. Well, now I want to try to get even more accurate. I can say, well, what's the slope of the secant line connecting 3 and 3.001? And I can say, well, that's the position at 3.001 minus the position at 3, which is only a change of 0.010001 units. When you divide that by 1/1000th, we're going to get our 10.001. So now, as you can see here, if we're trying to think about what's happening at 3, well, what's happening at 3 is going to be the limiting value of all of these intervals where the distance gets smaller and smaller and smaller. You're narrowing in on 3. So I can say, well, as that second point gets closer and closer and closer to 3, my y value, or I should say my slope, is getting closer and closer to 10. So I already know if I say, well, what if the second point is 3.0001? Then this answer is going to be 10.0001. It's going to keep on adding a 0 between here and this 1. So I can say, well, then my limiting value, the closer I get to x equals 3 is 10. This is going to be my instantaneous rate of change at x equals 3. So now, if I wanted to go back on my previous graph now, I could draw in a line tangent to this curve, and I didn't, but if I wanted to draw a line that just touches this quadratic at one point, and it takes on that slope forever and ever and ever, it would be a line with slope 10. That's what we just determined right here. When you take the secant slope of a point getting closer and closer and closer to a specific value, we're using the slope of the secant lines. So all of these are slopes of the secant lines, but each of those slopes of the secant lines, as their interval gets smaller and smaller and smaller, it's going to allow you to find out what the slope of the tangent line is, which takes on the exact slope of your function at any one instant in time. So I can say the slope of the line tangent to f of x at x equals 3 has a slope of 10. And the two big things I want you to really remember from this section: the slope of a secant line, that's a line connecting 2 points on a curve, that always will give you the average rate of change over some period. If you want the slope of a tangent line, and the tangent line here would only touch the graph at this one point and go up with a slope of 10 forever, then I could say, well, then the slope of the tangent line is going to give you the instantaneous rate of change at a specific x value. Okay, guys, that will do it for this section 2.1. Please do try your homework, and remember, I've worked all of the achieved problems, so should you run into any problems with them, look at what I've done, and of course, as always, let me know if you need any help.